Okay, so this little podcast explains variance reduction in Monte Carlo methods, particularly in integration. Okay, so in the lecture we introduced the idea of Monte Carlo methods, which are particularly useful for computing multidimensional integrals, and multidimensional integrals are required in many applications such as in computational finance and physics. In this lecture I review variance reduction techniques. So if we consider this basic integral here, I want to compute the integral between 1 and 0, the integrand f. We can use the fact that this integral can also be written as the expectation value of fu, where u are random numbers drawn uniformly between 0 and 1. So we get the estimate of this integral, alpha, is approximately the mean of applying the integrand function to the random numbers distributed between 0 and 1. So also from statistics theory we get an estimate of the error. It's very useful to have an error. So error goes like A, where A is related to the sample standard deviation, and root n, where n is the number of samples. And what this podcast, or this lecture is about, is reducing this A value. And also it's A smaller than the error is smaller for a given number of samples. Okay, as part of this, we'll see a more general formula for the Monte Carlo integration. So we started off by just looking at uniform random numbers, but actually the formula is more general. So if we have, we can break down the integral, which is broken into two parts: fx times hx. If we take hx as a probability distribution, then if we draw random numbers from the hx probability distribution, then we can estimate the mean of, we can estimate the integral by applying the f function to the random numbers xi generated from the hx probability distribution. Right, so this is just another way of writing from standard statistics. And obviously hx has to be a probability distribution, this means it has to be positive. And also there's an assumption of the normalization that this hx, when you sum over all space, is equal to 1. If hx doesn't have the correct normalization, then you can kind of correct for it by putting this v factor in the summation formula. And we'll see this formula is useful later on when we do stratified sampling, because there, if we're integrating between 0 and a half, this v factor will be a half. So we'll see some later examples where this normalization factor comes around. Okay, so we're trying to do an integral. Now we're going to look at something called importance sampling. So we just do the motivation. If we're trying to compute this integral, alpha, between fx dx between 1 and 0. If we have an example like this, where we have the integral of x squared plus 3 times e to the minus x squared divided by 2. I mean, because of this minus x squared divided by 2, this makes you think that maybe using random numbers from the normal distribution would be a good thing to do. And in this bottom example, we have the integral between 0 and infinity of 1 plus sine x times e to the minus x. Because of this e to the minus x factor, this suggests that it may be good to use the exponential distribution to generate the random numbers, and then you'd use the 1 plus sine x as the function to measure. Okay, these are things that suggest you have to really test these things, and sometimes this is more an art than a science, it feels like. Okay, so we look at this, consider the integral below, the upper integral, so this integral depends on L, and I'm just going to vary the length because it changes the kind of properties of the integral. So obviously we can do this by hand. So the same thing is we're just testing some of the ideas in one dimension, but in reality these Monte Carlo methods and various reduction methods are mostly useful in multi-dimensions. So the integral can be estimated using the Monte Carlo method. So if we just use from uniform random numbers, this L thing is the volume factor that I told you before. So you can use it by IL is L divided by N, where N is the number of Monte Carlo samples, the sum of e to the minus yi, where ii is a random number randomly distributed between 0 and L. So we can first set an integral L equals 2 with 5 samples, and here we're just looking at the numbers. So here are my random numbers: minus 0.61, minus 0.184, minus 1.1618. And then when you take the exponentials, there is some variation in this thing, but it's not too bad. You can compute the mean and the error is about 0.24, so like sort of 25% almost error, and this agrees statistically with the exact value you can do. So we're just testing methods at the moment. Okay, so if we go for a higher upper limit, so now instead of L equals 2, we do L equals 10, and so we do random numbers distributed between 0 and L equals 10, we have 5 samples. Now when we do the random numbers, because it's exponential, the numbers vary by a wide margin. And that's just because we're doing an integral between 0 and 10. So when you put in the exponential, numbers vary a lot. So the Monte Carlo estimate is now 1.19 plus or minus 6, plus or minus 0.61 or 0.62. So essentially we've got 60% errors. So that's not a very useful estimate compared to the exact result. And the problem is because this integrand is exponential, when you put in the random numbers, they vary over a big thing, so the variance is big just for these numbers. Okay, to get around that, let's try and use an exponential distribution. The one thing we're going to do is an exponential distribution is works from 0 to infinity. So when we do this integral, so we're doing the integral between 0 and 2, L equals 2. Here's the Monte Carlo, number of samples. So here, this thing Rx generates a random number from the exponential distribution. Because we're doing the integral between 0 and 2, if the random number is greater than 2, then we set it to 0, and that's the way to cut off the cut off the Monte Carlo. So it just does integral between 0 and 2 to get the right normalization. And then because the random numbers are generated at e to the minus x probability exponential distribution, the actual function is 1. So this is what this statement does. You generate a random number. If it's greater than L, in this case 2, it's 0 because it's outside the integration range. If it's less than 2, it's inside the integration range. And then we store a vector of these terms, take the mean, compute the error standard deviation divided by the square root of the number of samples, the error on the mean. That's what this does. Okay, so in this example we have a hit. So now we're doing this integral from the exponential distribution with 5 samples as before, and we end up with these random numbers. So this number is less than 2, this number is less than 2, this number is less than 2, this number is bigger than 2, so it gets mapped to 0. This one's less than 2, it gets mapped to 1. So when we compute the estimate, the error is 0.8 plus or minus 0.2, and compared to the exact error, 0.86. So that's not too different from using uniform random numbers. We have now about a 20% error roughly, so that's probably the same. However, when we do the calculation again for the for 10 samples, here we're computing this integral between 0 and 10, and we're using random numbers from the exponential distribution. So here are my random numbers. All the numbers are under 10, so they all get mapped to 1. Take the mean divided by 5. Then the Monte Carlo estimate is 1 plus or minus 0. In this case, there's no variation, and we're very close to the exact value. But what's happened here, whereas before when we use uniform random numbers between 0 and 1, there was a big variation in the numbers, and when we did the variance, we had a 60% error. Now we have a 0 error. So this kind of motivates the fact that if you have random numbers with a good distribution, you can do a drastic reduction in the error. Okay, so that's the basic idea in variance reduction. If the numbers in the integrand, which you apply the random numbers to, were all the same magnitude, this will help reduce the variance. So one way to do this is to generate numbers from a good probability distribution. Later on we'll see another method called stratified sampling, where we break the integration range up. Okay, so we're trying to compute an integral, so A and B Rx. You can break this into a probability distribution, fx, and something to measure. And so the idea is to try and choose probability distribution fx that minimizes the variance of hx. And this thing is not unique. You can do other probability distributions. So if you want to use random numbers from Sx, you just divide h by s, and then have Sx, and then just trivially the integral looks like this, hf divided by Sx, and then the Monte Carlo simulation, you generate numbers from Sx, and then the integral is actually h, applying h to the random numbers from Sx times f applied to the numbers from Sx divided by the random numbers from S and Yx. And for Sx to be a probability distribution, this thing should never be 0. Okay, so let's see an example. So here's an example trying to compute this integral. I equals 1 to 0, e to the minus x, 1 plus x squared. You can do, you can either use uniform random numbers. This is this probability distribution. You can use exponential probability numbers, e to the minus x, and then you sort of measure 1 plus x squared. And also you can find out that you can use the probability distribution for 1 plus x squared divided by 1 between x and 1. And then this gives you you can generate random numbers like this. And then this is another probability distribution to check. These things are not kind of unique. So we've already seen how to generate Monte Carlo integration with random numbers between 0 and 1. So let's do it with the exponentials. So integrating the region between 1 and 0. So we loop over the number of samples. That is, x is a vector with n sample entries. So we generate a random number from the exponential distribution. That's what this line here does. So we had to import. If the random number is bigger than the integration range 1, we set the vector to 0, the vector element to 0. If it's inside the integration range less than 1, then we set it equal to 1 plus 1 divided by r squared plus 2. So this is the other part of the integrand. And then once you have these random numbers, we take the mean, compute the standard deviation, divide by the square root of the number of samples. Okay, the similar idea if we're doing importance sampling the 1 over 1 plus x squared distribution. So in this case, we do the same thing. We compute the vector of to store the functions evaluated on the random numbers. We generate a uniform random number, and then to generate the numbers from the 1 plus 1x squared distribution, we apply a transformation. This is kind of pulled from an example. We don't really need to go in. So this produces numbers distributed equal to 1 plus x squared, but also suitably normalized. And in this case, if the number is greater than the integration range, set it equals 0. Otherwise, now the 1 plus x squared is part of the random numbers. So the e to the minus x is the function, and then this multiplies as a kind of normalization factor. And so in this case, we're splitting up the integral e to the minus x divided by 1 plus x squared. So we're generating random numbers from 1 plus x squared, and then the actual apply the random numbers to the exponential of minus rx trans. So rx trans has a probability distribution of 1 over 1 plus x with some normalization factors. And then the same thing, once we've generated the function applied to the random numbers, we take the mean to get the central value, and then more importantly, we have to compute the error, which is the standard deviation divided by the square root of the samples. Okay, so here's a summary of the different numbers. Again, we can also do the integral with an efficient quadrature. This gives us some idea. So these tend to be more accurate in one dimension. They're much harder to do in higher dimensions. So that gives us the number. If we do a standard just Monte Carlo estimate just with random numbers between 0 and 1, we get 0.5244, an error of 0.0677. And that's consistent with the number at the top. If you use exponential random numbers, we get 0.5326, an error of 0.129. So in this case, the actual random numbers have actually, using exponential random numbers, has not decreased the error over using just random numbers between 0 and 1. And then if you use random numbers from the 1 plus x squared distribution, we get, I got the result of 0.5320 plus or minus 0.045. So this 0.0045 is much smaller than this random number, just using the random numbers from just between 1 and 0. So because this has the smaller errors, using random numbers from 1 plus x squared is the best way. And note, all these things get consistent. All these numbers should be consistent within sort of 1 or 2 error values, well, 3 error values, because we're just doing different methods to compute the same thing. But because this method has the smallest error, this is the way. This is the one you'd use to put more of your computer time in. And it's not obvious these things. So in this case, it wasn't obvious that the exponential wouldn't be better than 1 plus x squared. So there's usually some experimentation in these importance examples, sampling examples. Okay, so last thing was something called importance sampling, where we try and use a clever probability distribution to generate the random numbers. Stratified sampling is actually just a basic idea. So we're trying to compute an integral between a and b. We can break the integral up into 2. So we can integrate from a to alpha and then alpha to b. And then we kind of Monte Carlo this integral independently and this integral independently. And this will give us, obviously, we'll get the final answer for the full integral is the sum of the 2 estimates in the 2 subregions. And then we can also estimate errors, and then we can add them together in quadrature to give us the error on the full integrand, on the full integral. Okay, so we use random numbers distributed between a and b. So this is the normalization factor I said at the beginning of the thing. So we're using uniform random numbers distributed between a and b. This is the normalization factor if b and a are not equal to 1. If b is not equal to 1 and a is not equal to 0. So we take the mean of the random numbers on top of the function. We can also break it down as into 2 integrals. And then we can do a Monte Carlo simulation for numbers between a and alpha, and then another Monte Carlo simulation between alpha and b. And because the cost of these calculations is the number of times the function is evaluated, when you do this, a lot of the time it's important to compare costs. So you don't just use the same number of samples in this thing, you use half the number of samples, because overall you want to use the same number of function evaluations to compare it against doing one Monte Carlo simulation for this. And it's not always obvious, but with some experimentation it can be that the error of breaking this integrand region into 2 can reduce the error. And if the error is reduced, you need less computer time. Okay, so let's go back to our integral. So we've done a couple of times using importance sampling this integral of e to the minus x divided by 1 plus x squared between 1 and 0. This time we're going to break it down into two regions, 0 and a half to 1. And we're going to do a separate Monte Carlo simulation for this part and this part. Okay, so this is what the code looks like. So I said, so this is like a function to call these things, so it brings the number of samples. As I said, because we're doing 2 Monte Carlo simulations, I divide n sample in by 2. This means that the actual number of integrand evaluations is the same as if we did the integral in 1. Because what you don't want to happen is the error to reduce because you've just used more samples when you break the thing down. So here we're trying to do the integral between 0 and a half. So we generate random numbers between 0 and a half. So this produces random numbers between 0 and 1. The half produces random numbers between 0 and a half. And then there's also this this volume factor I mentioned at the beginning. This is 0.5 times integrand. So we store a vector of these variables. So this is the mean of the first integral between 0 and a half. And then we can compute the standard deviation with the number of samples. We can then repeat this the second integral. This is the integral between a half and 1. So here we're generating random numbers between a half and 1. So NP not random is a random number between 0 and 1. When you put it in the expression, you get random numbers between a half and 1. So here we store the vector. Then this half thing is the normalization factor I mentioned on the first couple of slides, because we're doing random numbers between between a half and 1. We have to also kind of adjust the normalization a bit. And so we can take the mean of these vectors and then compute the error. Then overall the mean of the full integral to 0 and 1 is just add the 2 means. And then you want to compute the error. It's important to have the error on these things. And you can do this by known as quadrature. You take the square root of the error on the first integral squared plus the error on the second integral squared. And that gives you the error. That gives you an estimate of what the error is on the full integral. Okay, so this is all rolled inside a function where you put in the number of samples. And so here's how I'd use it. Remember, we're computing e to the minus x divided by 1 plus x squared. So this is the integrand. And so here I'm calling the estimate, I've got it stratified 2 because I've broken the integral into two things. And I've also computed the integral using the more efficient thing in 1 dimensions, this quad function from the scipad.integrate library. Okay, so the integral between 0 and 1 using the quad function, which doesn't use random numbers, is 0.5248. And then with the 124, we get 0.5279. It's consistent with the more accurate number for integration. And we get a reasonable error. I think if we look back, the actual importance sampling using the 1 plus x squared, numbers from the 1 plus x squared probability distribution is more accurate. Okay, so we've broken this up into 2 integration regimes. It can be useful to break it up into 4 or split it non-uniformly. Instead of between 0.5 and half and 1, you could do 0 to 0.25 and then 0.25 to 1. There's some kind of experimentation in these things. And okay, so as you probably noticed, I can't give you a procedure to get a very accurate what's the best way to do this variance reduction. There's either doing stratified or importance sampling. So it does require some experimentation. And you kind of hope that some of the computer would do more of the work for you. So one of the standard packages for doing multi-dimensional integration is a package called Vegas, developed by Peter Lepage in the late 70s. And this actually does it computes a probability distribution and then does some measurements and then adjusts it. So it's more kind of adaptive. So you don't have to mess around. And you can tell it's a kind of useful, it's been used by a lot of people when I pull this out. So this tells you it's been cited by 865 papers, and that's a good number. So it has a lot of practical applications. And the other thing, so we talked about variance reduction. This means that the error goes like a constant divided by the number of samples, the square root of the number of samples. So you'll quite often see in computational finance things called quasi-random numbers, and they're used a lot for integration regions up to sort of around 30-dimensional integrals. And here somehow they're a specially designed sequence of numbers, and they claim for smaller dimensions you can get sometimes performance 1 over the number of samples, so there's no square root, so the error goes down a lot faster. This is the error, is 1 over the number of samples. So that's better than the 1 over the square root of the number of samples from Monte Carlo. And I just have a plot here of 2 dimensions, what the numbers look like. So here's the random samples, and these are the snowball numbers. And here you can see they're not random; they're sort of been designed. But it's claimed they're quite an efficient way to do multi-dimensional integrals. Okay, so in this lecture I reviewed some of the ways of reducing the variance of Monte Carlo estimates, importance sampling and stratified sampling. Some of the sample Python codes will be online and available rather than copying from the PDF, and this PDF will also be available online.